Hello and welcome to my talk titled Supercharge Your JavaScript with WebAssembly. My name is Tamas and I work as a Senior Developer Experience Engineer at a company called Cloudinary. Furthermore, you also see my various contact details on this slide. Please feel free to follow me on Twitter. So today I'm going to talk to you about WebAssembly, and in order to get started we need to go back a couple of years and we need to take a look at this very simplified view of the web platform. So think about it this way: you have your browser and your browser is capable of executing JavaScript code. You write some JavaScript and that magically does its thing inside the browser. So there's this virtual machine in the browser itself that is capable of executing, interpreting, and doing all sorts of magical things with your JavaScript code. And this is what is available in the browsers today, and it was available for a couple of years now. And it's going to be an important point that I'm going to make to you later on with regards to this particular slide. Now, there's no denying in the fact that the web is growing at an incredible rate. So the things that we release, the things that we consume are highly performant. They try to achieve a lot of things. You know, we try to use video, we try to do a lot of processing inside these browsers and on the web. And essentially, the main language that we use is JavaScript. And we just try to push JavaScript to its limit. And in fact, let me just rephrase this sentence, and I'm going to rephrase it to say we push a language well outside its comfort zone. Now, if you remember, JavaScript was not really intended to be the main programming language of the web, and now there are a vast number of frameworks and other tools and libraries that rely heavily on JavaScript, but that wasn't the intention. Now, JavaScript is, a beautiful language, don't get me wrong. And all these features in the browsers are trying to get the most out of the language. The language is still evolving, which is a good thing, but there are some things that JavaScript is not really good at, and probably it will never be good at. Things like heavy processing things, CPU heavy tasks and so on and so forth. So all these low level tasks are either too complex or they could introduce some performance bottlenecks inside your application. And of course, I mentioned that before, but let me just say that again, that all the V8 and these other compilers that you have inside your browsers are doing an amazing things to do performance optimization. But sometimes you just can't do it because of the way how JavaScript is written. So of course, thinking about this, there must be a better way to allow low-level access and fast code execution at the same time, right? So it's, there may be a use case where JavaScript is just not good enough and you need something that has lower level access than JavaScript, performs better than JavaScript, and so on and so forth. And this is when we need to say hi to WebAssembly. So WebAssembly is something that wasn't introduced recently. In fact, here's a little timeline and a historic overview for you. Back in 2013, I believe it was the Mozilla Labs who created asm.js, which really just allowed us to execute code written in C on the web. Okay, now WebAssembly 2 years later had its first announcement. Another 2 years after that, an MVP was created, and believe it or not, since 2019, WebAssembly is part of the official W3C recommendation list. So HTML, CSS, JavaScript, and since 2019, WebAssembly is also part of the recommendation list. And what is WebAssembly? Now, if you go to the MDN documentation, which I really like, you will find a very good paragraph that describes what WebAssembly is, but it's a relatively complex paragraph. And so I came up with my much simpler explanation as to what WebAssembly is. And very simply put, it allows you to execute non-web-based code at near native speed on the web. Okay, so it allows us to have an application written in C++ and then be able to run that inside the browser itself. So we're going to take a look at an examples of this later on. Now, what is this connection between JavaScript and WebAssembly? So there's this thing called the WebAssembly JavaScript API. And oftentimes I hear that people say, well, WebAssembly is the next JavaScript, it's going to eliminate JavaScript, it's going to take over the web, and JavaScript is going to be diminished and forgotten. And these things couldn't be further from the truth, because JavaScript and the WebAssembly actually complement each other, okay? And they do this by the WebAssembly JavaScript API, which is a set of functions and a set of functionality that allows you to consume WebAssembly modules from within your JavaScript application or from within your web application. And what this allows you to do is to essentially use the power that comes with WebAssembly and utilize the flexibility that you are used to when working with JavaScript. So to me, this is an ideal mix between the two worlds. So the question is, how do you actually create a WebAssembly module? What is the process that you need to go through if you want to use the WebAssembly JavaScript API, you want to do something in WebAssembly? How would that look like? So here's a simple example for you. So you write some code in a native language, okay? And this could be C, C++, and a number of other languages. And here's a very simple example for you, where we have a square method written in C, takes an integer as a parameter and then returns that number squared. Very, very simple. Now what we need to do, we also need to install a tool called mscripton. Okay, and to install that, it's relatively simple. You just go to mscripton.org. I think that's the website. You set it up to your machine, and then you will have access to the emcc command line tool, which is the mscripton compiler. And then you essentially take your C file, you specify a number of options, and notice wasm equals to 1, and then you have some extra exported runtime methods in here. And then you have the -o square.js. So you essentially run this command, which is then going to create two things for you. It is going to generate a square.js file, and it's going to create a square.wasm file. The wasm file is going to be a WebAssembly module. And what is the square.js then? So the square.js is what you would call a glue code. So that code is used to tie the WebAssembly module together with JavaScript so that you drop that JS file into your application or into your web app, and then you will be able to access the methods that you have exposed from your C function, from your C application even. So all you need to do now is load WebAssembly via JavaScript, and this is how you would do that. And notice I'm using module.onTheRuntime initialized. I have access to that because I've added that glue code square.js to my app. And there are a number of ways that you can do this, and this is just a very simple way of accessing the WebAssembly module and the function that we have in C, just to save some screener state here. So I created an API object where I have a calculate square method that actually references the in-square method that I have specified inside my C file. And then notice that for the event listener for the button, I can go ahead and just write regular JavaScript. I can take a number from an input field and I can send that to api.calculateSquare, which is then going to do the squaring of the number using the WebAssembly module, right? Now, before you tell me that you can square numbers in JavaScript, I am very well aware of that. But the point here is to just show you how easy it is to have something in C and then bring it to the web using mscripton and WebAssembly modules. Okay, and then the last step is, of course, you just need to run your web app. And as a final reminder, just remember to always use the glue code. So that's the code that these compilers like the EMCC and some others would produce, because if you don't add that to your application, then you won't be able to interact with the WebAssembly module, or life is going to be a lot more difficult. Also, if you're doing a progressive web app that may use a WebAssembly module, just make sure that you add the glue code as part of your cached offline assets as well. Okay, so on this note, non-LLVM languages, so a language like Go, work slightly differently. So if you are a Go developer, or you're familiar with the Go programming language, then just know that you can also compile your Go project to a WebAssembly module. So Go has a compilation target for WebAssembly. However, things will be slightly different. Now, I have an example of this where I'm going to highlight the differences for you. And actually with Go, the glue code is something that you need to download from either the Go website or from their GitHub repositories. And with Go, you can actually have direct DOM access from your Go project as well. So it's slightly different than how a C or a C++ project would work. Now, of course, why would you want to use WebAssembly? You know, why would you want to choose this technology for your next project? That's a very good question. And I tried to select a couple of points that either I have used or I heard other say as valid use cases. So reusing existing code, I think that's a very straightforward one, because you have, you know, maybe an older C or C++ project that you want to, you know, now run on the web. Maybe it does some audio manipulation, some video manipulation, image manipulation, something that is very, you know, low level processing that you really don't want to recreate in JavaScript, or you cannot recreate it in JavaScript. You can just port those to the web. Predictable performance is an interesting one. I would talk about that in combination with the binary size. So when you have some JavaScript file and, you know, the V8 engine runs through with its magic on top of that, you get various performance optimizations, but those happen kind of on the fly. Whereas with the WebAssembly module, because of the static typing and the way how you just create a WebAssembly module, your performance is always going to be the same. There is not going to be varying levels of performances based on how your entire application is written, right? So the performance and the binary size of the WebAssembly module is always going to be the same. So it's a given, it's not going to change. And the last use case could be where you want to have some advanced system access. So maybe, you know, want to run threads, you want to do SIMD, you want to have shared memory. So all these advanced features that you do not have currently in JavaScript, then WebAssembly is a very good option for those. In fact, in a recent project, I was using two versions of the WebAssembly module for the OpenCV library. One was with SIMD enabled and the other one was without SIMD, and I could achieve double the FPS for a video-based project that I was working on. So you see the difference is significant in there as well. So putting all of this together, this is how the web platform looks today. So if you know, we take a look at this very simplified view again, what's happening inside our browsers, we have a virtual machine, but that virtual machine is now capable of executing both our JavaScript and our WebAssembly code. And that's how it is today. As I said, it's official. It's part of most of the modern browsers. In fact, I think all of the modern browsers now support this. So feel free to experiment with WebAssembly today. So let me show you a couple of demos as well, and I'm hoping that they will be successful. So I'm going to show you two projects. One is a C++ port to the web using WebAssembly, and the other one is a Go project. So let's start with the C++ project here. So let me just open a browser as well. Okay, so Simulacra is, as you can see, a C++ file, and Simulacra is short for Structural Similarity Unveiling Local and Compression Related Artifacts. Very, very simply put, this C++ project is able to tell us if the same two images look and feel the same based on their quality. And at Cloudinary, we use this particular technology to determine if the quality reduction of an image is actually going to be visible to the human eye. Okay, and this is a C++ project. It was, you know, it has always been a C++ project. It basically asks you to compile this. You will get a Simulacra binary, and then parameter 1 in your CLI should be the first image, and then parameter 2 is going to be the second image that you want to compare, and then Simulacra is going to return you a number. And as you can see here, if the number is 1 or close to 1, those are very different images. So you will have some very visible quality differences inside the image. Generally speaking, anything below 0.1 should not be visible to the human eye. Now, I thought this is a great project. Why don't we have a web version of this? And so what I had to do was, of course, port this to WebAssembly. I used mscripten to do this. I actually wrote a blog post about this, so if you're curious, you can take a look at how this whole project was ported from C++ to WebAssembly. But what I have here, once I have the WebAssembly module and the glue code, I could very easily just load the WebAssembly module. And what I'm doing is grabbing two images, and notice that I have this write file method here. So when you use WebAssembly, you get access to the browser's virtual file system where you can write and read files from. So that's another very interesting use case. So I'm writing the two images, and then I do the simulacra calculation for both, and then I just return that. And I built a very simple UI for this particular tool. So what we can do, we can fire up an HTTP server, and then I'm going to go to my browser and just open up port 8999, and then we're going to take a look at how this project looks like. Actually, before I do that, let me just copy this particular image, and you will notice that this is an image of a car. So this is the unmodified 100% quality, highest quality version of the image. And what I'm going to compare it with is Q_1, which is of course going to reduce the quality of the image to quality 1. So it's going to be very, very pixelated. So you see, this is a terrible, terrible looking image. Now at Cloudinary, we have a feature called Q-Auto, which is automatically going to reduce the quality of the image in a way that is not visible to the human eye. So if I put Q-Auto, then you will get, again, a high quality version of this image. But the difference is that if I take a look at the network panel here real quick, and if I try to also zoom in a little bit here for you, you will notice that this particular image is 732 kilobytes in size, but if I remove the Q-Auto, so if I take a look at the original, then that's 1.4 megabytes. Just by adding Q-Auto, we shaved 50% off from that image. But the question is, can we see the difference? So if I put the same two URLs in here, then we're going to be getting a 0, indicating that these images are exactly the same. If I put Q_1, then I should get a very high number, a number close to 1, so 0.4. And as I said, anything above 0.1 means that humans will have perceivable quality differences between the images. And let's finally verify Q_auto, and that is 0.03. So in fact, this tool tells us that these two images do not have any sort of artifacts that the human beings would in fact see. So this is the C++ project running in my browser because I was able to pull this from C++ to WebAssembly and then add it to the web. So that's one of the use cases. Now the other project that I wanted to show you is a project that was written in Go. So in the same way how Cloudinary has Q-Auto to automatically reduce the quality of the image, we also have F-Auto, which is short for automatic format. So based on the browser that you're using, we can select the appropriate image format or the best image format for that browser based on the analysis of the image as well. And of course, you can take a look at this inside your browser. So let's go back to this image. And if I now open up the network panel, and if I just do an F-Auto in here, so I do F_auto, then let's take a look at the headers. So this is a JPEG, but if I shrink this down to say width 500, so this is a 500 pixel version of this image, then because I'm using a Chrome browser, I am now getting a WebP image. And I thought this is great, but I would like to further analyze the image itself. So how could I do that? And well, the answer was that I created this Go project where I used some libraries like libwebp and libpng and some others to further analyze the images that are returned from Cloudinary. So as opposed to just saying that, hey, this is a WebP, I can now tell whether it's a WebP with an alpha channel. What is the container for that WebP image? Is it, you know, a VP8, a VP8L, so on and so forth. If it's a PNG, I was able to, you know, analyze the bit depth, you know, what kind of interlacing it has, and so on and so forth. And I mentioned that Go works slightly differently. So notice this wasm_exec.js file, which is essentially my glue code. And then I have main.go, where if you take a look at a line like this one, even though this is a Go file, this file looks really familiar, right? Even if you've never seen Go, but you know JavaScript. So this is essentially saying document, get element by ID, response text, and then set the inner HTML to something. So I can essentially manipulate my DOM from within my Go context, which is very, very useful. And then executing this very simple command, I was able to build the WebAssembly version of this Go project. So let's take a look at how this looks like by opening up another server. So that's port 9999. And this is my project. So this is that f-auto flag already in here. So let's add width 500, and let's use the built-in user agent, which is in fact going to be a Chrome. So let's hit check. And this is a lossy WebP with a VP8 container that has no alpha channel. But what if I go to say gem/darthvader.png? Well, let's see, what do we get? Okay, so this is now a VP8X container that is lossy, and it does have an alpha channel. Okay, this is perfect. So let's see what happens if I just refresh. If I use f-auto with 500 with a browser that does not support WebP. Now, here's a sort of additional trick for you. You can actually change the user agent by using the network conditions panel using the developer tools in Chrome. And I'm going to just say that I am now on a Safari Mac. Safari Mac does not support WebP. So let's see what happens if I call the same image. Well, it just returns a JPEG image. Or if I remove the width 500, is it still going to be a JPEG? No, now it is a JPEG 2000, which is in fact an image format supported by the Safari browser. So this particular tool allows me to dig one level deeper and analyze these images further. And I could have taken this to the you know, a whole different level by just manipulating the Go code. So I'm going to leave you with some resources. Take a look at the various projects that are out there. You know, someone ported Doom via WebAssembly to browsers. Squoosh.app is one of the flagship applications that is done by Google. There are lots of case studies around it. They talk about it quite often. And behind the scenes, that also uses WebAssembly modules. So take a look at these resources. They're very, very useful. And I hope you found this presentation to be useful. And thank you very much for attending this session, and I hope you will have the opportunity to try out WebAssembly in the not so distant future. My contact details are on the bottom of the slide, so please feel free to contact me at any point in time if you have any questions or you'd like to know a little bit more about WebAssembly. Thank you.